In this problem-solving session, we're going to look at the predominance domains. Okay, in particular, we're going to look at question number 11, which just asks for the predominant species present at a particular pH. Then question 10, which asks for all the concentration of species at a particular pH. Then I'm going to solve for you a concours question 2018, which looks at predominant species. And then number 40, which I said I will solve for, that's for the preparation of buffers. And that's using a triacid in the presence reacting with OH minus to get a buffer of a particular pH. Okay, so in the first question, number 11, they gave us, given the pKa values of a polyprotic H3PO4, and they gave us the pKa values, which of the following statements are correct? Now, before we start, what you should do is the following. Draw, if you're just asked for which is the major species, draw your predominance diagram in the following way. Put a straight line with pH, and then put the pKa values separate. 1, 2, 3. I have 3 lines for the pKa values, pKa1, pKa2, pKa3. Then at the area below pKa1, put the most acidic species, which is H3PO4. And then in this area and the next, between pKa1, pKa2, put H2PO4, then the next species, HPO4 2-, and then the final species, PO4 3-. So we're separating all 4 H3PO4 species with their pKa, with the pKa. Okay, so that's the easiest way to draw the diagram. That's what you would do first. Okay, now let's answer these questions. Okay, the pKa2 is associated with H3PO4, PO4 3- couple. Well, to begin with, the H3PO4, PO4 3- are not a couple. Remember, a couple is the acid and its conjugate. All right, that's automatically wrong. I don't have to think further. pKa1 is associated with the H3PO4, H2PO4- couple. Yes, this is the acid, that's its conjugate base. And indeed, that's the first dissociation of the H3A species, and it's governed by a pKa1. That's correct. At pH 1, PO4 3- predominates. So I didn't really need this predominance diagram until I get to these types of questions. At pH 1, okay, so where is pH 1? Oh, there it is. It's below pKa1. So I'm here. And if I'm here, look at my arrow. If I'm here, do I have PO4 3-? No, I don't. So the answer is wrong. At pH 8, HPO4 2- is predominant. So let me go to the predominance diagram to pH 8. Where am I? Oh, it's around here somewhere. What's my species that predominates? Look at this. It's the HPO4 2-. So is this correct? Yes, it is. D is correct. At pH 10, so let me go to pH 10. Where is that? Well, it's somewhere in this area. Okay, so it's mainly here, maybe. PO4 3- predominates. Do I see PO4 3-? No, I don't. Okay, it's after 12.1, PO4 3- predominates. And therefore, that is incorrect. So it's very easy to do this, and that's the only diagram that you need. You don't need more details on this predominance diagram. That's really the easiest predominance diagram. Just separate by pKa values and put the species. Acidic, most acidic at the lowest pH, hot, and at the highest pH, the most basic species. All right, so the answer for this is really B and D. Now, just of course, you all know that at pKa1, we have equal concentrations of H3PO4 and H2PO4. And I just want to make that clear for the next question. So at pKa2, we have equal concentration of this species and that one, and at pKa3 of this species and that. Now, if you're asked to calculate the concentration of all the species at a particular specified pH, that's when you really need a more detailed predominance diagram. So let's look at now question number 10. Question number 10 reads, to a phosphoric acid solution, H3PO4, I'm given the concentration, we progressively add sodium hydroxide without changing the volume. So we're adding it as a solid and we're assuming volume doesn't change until the pH of 9.5, okay? Determine the concentration of the phosphoric species present in the solution. And of course, you're given the pKa values for the H3PO4. All right. Notice sometimes we have different pKa values given, and we have to watch out. Don't memorize pKa values. So for here, sometimes we see it 2.1. Sometimes I see it 2.2. Again, that's at 2.1. I'm not sure. And this is of 12.1. And let me pause this. Okay, so indeed, there's a little bit of a difference in pKa values between number 10 and 11. That's not the nicest thing to do, but use the pKa values that are given. Okay, so I first have to draw out my predominance diagram. And I draw out the simplest predominance diagram possible initially, okay? So I put the pKa values, align, pKa1, align, pKa2, align, pKa3, that's your pH. Then I put the most acidic species at the lowest pH, H3PO4, then H2PO4, HPO4 2 minus, and PO4 3 minus, okay? Now, at pH 9.5, what is my predominant species? Yes, it is. The predominant species is HPO4 2 minus. That is all you have to do if you're just asked for what is the predominant species. Do not do beyond that. Don't get yourself into further calculation. But in this question, that was not what was the question asked. They asked for the numerical concentration of all species needed, okay? And thus, you need much more further calculations, or you need further calculations, okay? So again, at pKa's, we have equal concentration of these two species, those two species, and these two species. So in this case, I need a much more detailed predominance diagram for the H3PO4, and that's what I'm going to draw for you now. And yes, unfortunately, you might have to go through and draw this, but you don't always have to put all the details depending on what you need. So I'm going to add some more pH values, which I can easily calculate, okay? And so in your mind here, guys, you're also thinking about the titration curve. That's the easiest way to think about it. The titration curve for the H3PO4 reaction with OH minus. So at the first equivalence point, remember all the H3PO4 gets converted to H2PO4 minus, right? Absolutely. And what is H2PO4 minus? It's an amphoteric species, and I can get its pH from half pKa1 plus pKa2, which equals to 4.7. At the second equivalence point, So at my second equivalence point, all the H2PO4 minus gets converted into HPO4 2 minus, which is also amphoteric, and I can also calculate the pH at that second equivalence to be half pKa2 plus pKa3. And now watch out for the pKa values. This HPO4 2 minus, remember, it acts as an acid or a base. So if it acts as an acid, it becomes PO4 3 minus, so you need pKa3. And if it acts as a base, it picks up a proton and it becomes H2PO4 minus, so you end up getting the two species with the pKa2. So a little bit, tricky, but watch out for it. Now, of course, you all know at pKa3, all the HPO4 minus becomes PO4 3 minus, but that's a little bit of a harder calculation because I need the concentration of PO4 3 minus, and I don't necessarily put it on my titration, on my predominance curve. I don't have to do that. So now I draw up a more detailed predominance curve, put a line with a pH. Yes, put your pKa1, pKa2, pKa3, but then also put a larger line here with the pH at equivalence, which is the amphoteric species half pKa1 plus pKa2. And put a larger line in between here, between pKa2 and pKa3, and that's half pKa2 plus pKa3, and that's the amphoteric species 9 HPO4 minus. And so if we start off with H3PO4 at 4.7 pH, we get only H2PO4 minus. And then at 9.65, I get only HPO4 2 minus. And of course, at a particular pH, which is, you might have to do a quadratic equation here, we only get the species PO4 3 minus. Clear? So these two pH values are critical pH values which you might need, and it would be, easy for you to do the calculation to get a detailed chart. Now, between H3PO4, where I only have H3PO4, and H2PO4, in between those two, we have a buffer region which houses both these species, where you get both of these species are present, and that region is governed by Henderson equation, pH equals pKa1 log of the base, H2PO4 minus, and H3PO4. And so, I could put for here what species you have, but automatically I just thought I may as well just put the Henderson, which means that you have both of these, H2PO4 and H3PO4. Likewise, between the total where I only have H2PO4 minus and I only have HPO4 2 minus, I also have a buffer region, which is governed by a Henderson with a pKa2. And in the third, where I'm in between the HPO4 2 minus and the PO4 3 minus, I'm governed by another Henderson, where I use pKa3 and these two species. Clear? Now you pretty much have not only, a more detailed, but also the pH, which is gonna govern. Why do I need this? Well, look at it now, okay? And I'm gonna show it to you. So this is a nice curve to memorize. Again, a little bit harder to draw, and you do need these two. And yes, it is different than the other one. The other one, I just put pKa1, pKa2, pKa3, and I just put here H3PO4 minus. Now, just a little pointer. Of course, you all know, like we said, pKa1 is where the concentration of H3PO4 equals H2PO4 minus. And so in this region, right between here and there, where the pH is greater than pKa1, who's the predominant species? Who is more? Yes, the more basic species, which is H2PO4 minus. And in this area where my pH is less than pKa1, the H3PO4, the more acidic species, will predominate, which goes back to that first diagram. Okay, now at pH 9.5, guys, if I drew this more detailed diagram, if I'm at pH 9.5, where am I? Well, I'm here, okay, which we already said that that's where my, I'm here, okay? And we said in that area, the HPO4 minus, the H2PO4 predominates, or that's what I said. Okay, so there's the 9.5. So this is a little bit more detail, which tells me that at pH 9.5, I actually have two major species, and their concentration is determined by, it has to fit into Henderson. Okay, so here's my 9.5. Okay, and thus at pH 9.5, I have governed by a buffer region, and we have the two species, HPO4 minus and H2PO4 minus. Okay. So if I have this equation and I know my pH is 9.5, I have pKa2, then I can get a ratio between HPO4 2 minus and H2PO4, or I can get each species on its own. Okay, so get this pH minus pKa2, so 9.5. This is 9.5 minus pKa2, which is 7.2. And that's 10 to the power of that number, you get 1.99. So now we have one equation with two concentration terms inside this equation. Now we have conservation of mass. Of course, you can use concentration here or number of moles, because remember in Henderson, the concentration and moles are pretty much the same because the volume, total volume cancels out. From the conservation of mass, the number of moles is conserved, or the mass is conserved. And the number of moles total of the H3PO4, which I start off with, is going to be split into all the different species in my solution. However, at a particular pH value, so for this case 9.5, the H2PO4 and the PO4 minus are essentially negligible relative to the other two species. Of course, we have them in solution due to the back reaction, but their concentrations can be assumed negligible. And if we actually, since we have the number of moles, and if the volume is conserved and doesn't change, then the concentration also equals to the number of, instead of number of moles, we can just simply put concentration. So we have 0.1 equals the concentration, that's the total concentration of H3PO4. That concentration of H3PO4 will be mainly split between the two species HPO4 2 minus and H2PO4 minus. Okay. And thus, we have two equations and two unknowns. Here's my two equations, two unknowns, and I can solve for these unknowns. Of course, if you look at this part, just look at it. HPO4 2 minus is some 200 times the amount of H2PO4 minus. So pretty much, it's the major species in my solution. And the total concentration of H3PO4 is pretty much HPO4 2 minus. Nonetheless, be a bit more detailed, and you get an exact value for the H2PO4 minus concentration. Okay, so we can solve the two equations, two unknowns, get the two species, and you are pretty much done with the two major species in your solution. Now, if you want all concentration of all the species, well, you have to go a little bit further. At pH 9.5, I could easily get the H3O plus concentration, which is simply 10 to the minus log of the pH. Get that number. Of course, you could also get OH minus if you really want in your solution. That's Kw divided by H3O plus, and get that number, okay? Or if you have pH, you can get POH, and the concentration of OH is 10 to the minus POH. Once you have the H plus concentration, we go ahead and we find H3PO4 in my solution. You could also use Henderson, by the way, for this, but we are going to use the Ka1 expression for the H3PO4. You can write the equation, but you should all already know this. The H3PO4, when it splits in water, it becomes H3O plus and H2PO4. And so the Ka expression is the following. All for H3PO4. Clear? We have H3O plus, that's right there, 10 to the minus 9.5. You have the concentration of H2PO4 minus in your solution, and you have your Ka1, which is 10 to the minus pKa1, and then simple calculator calculation. If you need PO4 3 minus, and most likely if you want all species, you will have to find it. Where do you get it from? Yes, you can get it from the Ka3 expression. Ka3 is the last dissociation of the HPO4 minus in water to PO4 3 minus, and that's the expression for it. And therefore, what do we have? You can solve for PO4 3 minus. PO4 3 minus becomes Ka3, which is 10 to the minus pKa3, times the HPO4 2 minus, which is the concentration which we found initially, which is approximately 0.1, give or take, and the H3O plus, which is 10 to the minus pH. Okay, so for that, that's a calculation in the calculator, and you get the number. Look at these numbers. Yes, indeed, they are small. Their concentrations are relatively low relative to the other two species. Okay. Now I just put a Ka2 here. I don't really need it because I used Henderson, but the Henderson just comes, by the way, just from the log of the Ka2 value. So you could have used here, instead of Henderson equation, you could have used the Ka2 expression. I think it's just easier to use Henderson in that case because you know it's a buffer region between those two species, and that's it. But if you use Ka2, you would get as well, if you have, that the concentration of your major species is HPO4 2 minus, and H, and of course you assumed here that all of the H3PO4 minus got converted into HPO4 2 minus, but that's an assumption on your part, and that's why I don't really like to use this equation. It's better to use two equations and two unknowns to get more detail. Okay, great. I'm going to leave this question up to you to solve. This is at pH 8.3, and they ask you for the concentration of all species present, and I will give you the solutions to this. Try it on your own, and you'll know yourself if you're getting the correct answer or not. And now I want to do a concours question, okay? And to let you know that sometimes you do a little bit more work than you have to, and on the concours you can't afford to do that. Okay, in 2018, this was a question. They asked for a tetraacid H4Y. Okay, so they gave you H4Y. What is the predominant species at pH equals to 8? Well, they gave you the pKa values for all the couples of the H4Y. So you have the pKa values, and they ask you what's the predominant species, and they only put a single species here. Now, if they put 2, you have to watch out. You have to be a little bit more detailed, and I'm going to show you how to do that. But they only put a single species in your MCQ. So what you do, you draw a straight line, pH, and one line for pKa1, pKa2, pKa3, pKa4. And you would say, in this area at lowest pH, we get the H4Y, the most acidic species, and you put all the other species after that. Very simple. Don't overdo it more than that. Then you ask yourself, at pH 8, where am I? Well, there's pH 6, and there you are. That's pH 8, that's 10. Well, approximately somewhere along those lines. I'm here somewhere, okay, in this area. What's my predominant species? That's it. It's HY3 minus. Clear? HY3 minus. You don't need the 2 species and the exact amount of the 2 species. Do you have more of this, more of that? You don't need that. Okay, now, that's all you need. So at pH 8, HY3 minus is predominant. And your answer will be, what is that? HYB, okay? Now, if you're asked for exact concentrations, that's when you need a little bit more detail on your diagram. And I usually put this diagram, and I don't really, I actually sit there and calculate the pH. If I'm in this region, I just put a line kind of in the middle where I only have, I say I only have my HY3 minus species. Okay? And that pH for that species is an amphiolite, and it will be half. And since I'm here, automatically look at my pKa, pKa3 plus pKa4. So it really helped me to recognize that in that region equals 8.2. So this pH where I only have HY3 minus is 8.2. And so if I'm close to 8, where am I? Am I in the buffer region between HY3 minus and Y4 minus, or am I in the buffer region between HY3 minus and H2Y2 minus? Yes, of course, you're in this region, okay? So you're here, you're not on this side, okay? So that's how you know which region you're in, and the buffer equation that you should use to calculate the 2 major species. And now your 2 major species in your solution is HY3 minus and H2Y2 minus. And of course, you're going to need another equation, which is the conservation of mass equation, and which tells you that the summation of all these species is equal to the initial concentration of your H4Y, and you cancel all the other species except these 2. Okay, you get 2 equations, 2 unknowns, and you could move on from there. Of course, that's if you're asked. Of course, I can go ahead and put all the half equivalents when I only have the H2Y species, and if I have that, I can do that, but I don't have to. Okay, I will just, you're putting more information than what you need. Number 40. Remember, I told you that this is actually a buffer preparation. They prepared a buffer using the triacid H3PO4, and they added NaOH. So let's read here. Determine the volume of base, VB, V, they said, of NaOH 0.5, which should be added to an initial volume 30 mils of a phosphoric acid H3PO4 with a concentration 0.1 in order to prepare a buffer at pH 7.5. you're given pKa values, I really wish they would stick to exact pKa values, or at least the same pKa values all the time. We don't. But anyway, okay, at pH 7.5, what do you guys have to do? Yes, unfortunately, guys, you can do two things. You know, at pH 7.5, I look at this and I'm saying, if I'm in that pH, what region, what would be the best two species to use to get a buffer of that 7.5? You don't have to really draw out a predominance diagram, okay? You don't have to. You ask yourself, okay, it's best to use a pH closest to the pKa, so it's better to use whatever species in the pKa2, and the two species in pKa2 are H2PO4 minus and HPO42 minus. Clear? Now, of course, you can draw a predominance diagram and a detailed one, and you would, you know, say to yourself, at pH 7.5, yes, I'm in the domain of H2PO4 and HPO42 minus. Then. So, okay, you're choosing a buffer with the pH 7.5. So you choose the pKa, which is closest to that, and therefore these are my two species. Okay, so 7.2 is closest to 7.5. So pH is going to be pKa2 plus log of the HPO42 minus divided by H2PO4. And now we have to go back and think about the titration diagram, okay? The quantity that of base at the first equivalence neutralizes what? All the H3A. So if I find the first equivalence point, that is the amount of base, OH minus, that I need to convert H3PO4 to the H2PO4 minus. So I go ahead and try to find that first equivalence. CAVA equals CB, V at equivalence. VB at, you have the concentration of the acid, you have the volume of the acid, which is H3PO4. You have the concentration of the base, which is 0.5. Find the V equivalence, and when you find it, it comes out to be 6 milliliters. Okay, so concentration volume was of H3PO4 was 30, and its concentration was 0.1. And just as a proof, of course, you don't need to do this diagram, but I'm just showing you that the H3PO4 first reacts completely with the OH minus at the first equivalence point, and you get equal number of moles after the addition of 6 milliliters, and all of these two get converted to H2PO4. Now, after that, I need to add more OH minus to get to this region, right? To a buffer region between H2PO4 and HPO42 minus. And so now I have another equation. I have to add more base. Remember VB prime. That's the amount of base after the equivalence, okay? After the first equivalence. So if I want more base after that, I call it VB prime, and that's required to react with the second acidity, H2A. So let's take this now equation. If I'm now reacting the H2PO4, which I originally started with 3 millimoles, how much OH minus should I add? That's concentration times the volume VB prime. And in order to get a buffer region, so I want my OH minus to be what? Limiting in this case. And so we let that equal to 0. The leftover H2PO4 will be 3 millimoles minus the 0.5 VB prime, and the produced H2PO4 will be 0.5 VB prime. Okay, so of course you have, you're in a buffer region, and now you have the concentration of HPO42 minus, which was produced, which was equal to the amount of OH minus limited. And you substitute that in, and there's leftover H2PO4, which is the original 3 millimoles minus the limited OH minus. concentration. Notice these OH minus concentration is in terms of VB prime. Now, if you go back and you had solved the problems for diacids, this becomes easy. And that's why I like to do these questions after we do all the titration examples. Okay. Okay, now what do we do? Well, the difference is now I have the pH, okay? I don't have VB. Okay, I don't have VB prime, but I have the pH, and so you have one unknown. Go ahead and solve it. Now it's a matter of your calculation. Take the 7.2 to the other side, get the anti-log of it, 10 to the 7.5 minus 7.2, and then you just have to do the rearrangements to get VB prime, and you get VB prime equals 4 mils. Okay. So what's the total volume of base added to the H3PO4 to get this buffer at pH 7.5? Total base added VB will be the volume at equivalence to get rid of all the H3PO4 plus the volume more OH added VB prime to go from the H2PO4 minus to an amount of HPO4 minus to get that pH of 7.5, which happens to be 4 mils. Clear? Of course, you could have done it a little bit differently. You could start off, I'm just going to go back here. You could start off with an equation of H3PO4 and then keep all the OH minus in excess. So with a total volume VB, but then you know that OH minus is in excess and your calculation differs slightly. I like to use the same method that we used with the titration questions, where we get rid of the VB, the first V at equivalence, and then you use the extra amount with the second equation, okay? So VB prime for the second equation. That covers all the questions. At least all the hard questions. If you have any questions, or if there's a question that we did not do or we did not cover, do let me know, but I think we covered all of the questions in your tutorial, okay? Let me just point out, this number 39, we already solved it, but this was also preparation of a buffer, but with a mono acid, okay? And remember we used, this is 39. In that question, you can go back to it, of course. In that question, they wanted to prepare a buffer of 1 liter, and we used volume 1 plus volume 2 equals 1 liter. And we were asked for what volume of each of these plus do I use. And so that's a little bit of a different style to solve than the number 40. But nonetheless, again, we're using the same type of equation, buffer equation, and then another equation here with 2 different volumes. So 2 equations, 2 unknowns. Go back to number 39 and do check out the difference. It is a little bit different.